So following on from the previous two videos, we've got to, well, we've worked out this probability. Now in this video, we're going to tackle this. So, so this one here, within the radius of 5 to 10. So 5 to 10 here, within this radius here, we've got to take the integral from 5 to 10. So remember, we are revolving this 360 along the y-axis. So it's really us revolving this around 360. That would then give us a hollow cylinder, if you like. So that would give us this thing here. Okay. So basically, it's us working out the volume of this and then dividing it by the whole thing here, which is from 0 to infinity. Well, now we are going to look at this. So we've done this. Now we are going to look at this. Okay, so in the previous video we worked out that to between 0 and 5 the probability is this. We've done that. So now we're going to look at the probability within a radius of 5 to 10. Within a radius of 5 to 10. That would mean us taking the integral from 5 to 10. Okay, so that will then it's really us looking at the volume of that hollow cylinder and then divided by the whole thing from 0 to infinity. So the probability is given by this, and now pi is a constant, take pi out, and then they will cancel each other off, giving you this. Okay, so now integrate this. That will then give you this, and then this here's a constant. Here's a constant. We can take it out, and that will then cancel each other off. It will then give you this. Okay, it will then give you this, and then from this it will be this. Take away this thing here. Okay, and then this thing. Take away this thing here. That will then give you this. Okay. And then that will then give you this. Okay, so the probability of us getting within a radius of 5 meters. So that's this bit here. So the probability of us hitting it within this region here would be 0.03. The probability of us hitting it within this region here. Remember, it's being revolved around 360. So within this region here would be given by this. Okay, so hang on. So the probability of us hitting the golf ball and it landing within this region here is given by this, and the probability of us hitting the cannonball and it landing within this region here is given by this. Now you might be wondering, it's a bit strange in that the probability graph is highest. Is highest within this region here, but yet the probability of us hitting within this region is less than the probability of us hitting within this ring here. The reason for that is because you've got to take area and probability into account. When you look at this graph here, you're just looking at the probability. You've got to take the area and the probability. You've got to take the area and the probability into account. Well, if you look at the ring here, if you look at this ring here, the area of the ring is a lot bigger than it's a lot bigger than the ring itself. So it's a lot bigger than this area here. So if you look at the let me just illustrate this again. So radius of 5. Let's just say it's this bit here. Radius of 5. Let's just say it's this radius here. It's this area here. Okay. Well, the area of the ring is a lot bigger than the area of this circle here. The area of the ring here is a lot bigger. You can see that here. It's a lot bigger here. So you've got a bigger area, even though the probability around this region, is a lot less. It's less than around here. But the thing is, the area is a lot bigger. So when you consider the probability, you've got to combine the probability graph with the area. You see, this area here is tiny. This area here is tiny in comparison to this ring. This ring here, the probability of you hitting within this ring is, granted, it's a lot less, but the area is a lot bigger. So you can see this ring here is a lot bigger than the circle here. So you've got to combine the probability and the area. You've got to take the area into account as well. Okay. So as it turns out, it's easier to hit it within this ring here than it is to get it within this spot here. Okay. And you may think that this here seems a bit low. So what you do is you approximate it. So this region here is, well, within 0 to 5. So within 0 to 5 here. So that's within this. So let's approximate it to a cylinder. Well, if you work out the area of this cylinder and then divide it by the area, let's approximate this to a cone. So hang on. So bear with me. Let me just move this across. Bear with me. So approximate this. So approximate this to a cone here. Approximate. Hang on. Approximate this to a cone here. Okay. So remember, you're considering the volume. So if you approximate this to a cone here, a cone would be the base times the height divided by 3. That's the volume of a cone. So the base here is really the circle here. So it would be pi r squared, pi r, but the r is from 0 to 60. The point I'm trying to make here is that this here seems a bit unrealistic. It seems a bit too low. So what you do is you get this cylinder here, the volume of this cylinder, approximate it to a volume of cylinder, which is pi r squared, r being 5 meters from here to here. So that would be 25 pi times the height. So the height here happens to be 1. The height here happens to be 1. So hang on. So approximate this to a cylinder. So that would be 25 pi times the height, which is 1, so it's just 25 pi, divided by the volume of this cone here. Approximate this to a cone, so that would be the radius of this thing here would be 60, so it would be pi well, it would be 36 pi here. So that 36 pi there will give you the area of the base of the cone. And then times the height, which is 1 times 1. So if you get the cylinder divided by the cone, it will actually give you, well, it will be approximately this thing here. Okay. And now if this thing here seems, so the point I'm trying to make here is that when you first glance at this value here seems a bit low, but if you approximate it to a cylinder and then divided by this approximate cone here, it will give you a value that's similar to this. Okay, so this is not an unrealistic answer.